So here we are again. Let's go. Let us play the next few levels. The first one is gonna be called Add 5. You have built your computer, but to win the competition, you still have to finish the maze. But since you don't know how to program it yet, you're not quite ready for that. So in the meantime, we will have you help out on the ship a little. Yes. Click on the added memory icon. These few levels are basically, I don't know, they are, and I recommend you to play them properly, mostly first alone, like before you watch these videos, which will basically give you answers to the problems and solve this. It is, I don't know, I think it might be way more beneficial for you to figure this out on your own. Maybe not. I have no idea. I don't know. You do you. Click on the added memory icon on the program component to start programming a computer. Yeah, what I was gonna say is that the next few levels are basically here to explain to you how all of this stuff works. I'm going to figure it out. To start programming your computer should read the input, add 5 to it, and output again. No need to worry about overflow. And we are going to program it by hand, which is going to be fun. Notice the immutable register components have been replaced with a custom component with identical functionality. Oh, interesting. I remember there was a version of this game. Let me just check this. Where do you sit? There you sit. Yeah, well, this is cool. We now have this custom component, this custom register, and I remember there was a version of the game that actually featured this 2 output register. I think I remember. Anyway, notice, yeah, have been removed, and like in the first version. In the first version of the game, this register plus was a custom component as well, but yeah, as I said, for a while there actually was an 8-bit component. There was this always out register. Anyways, let's start with the level. So yeah, we're going to program it directly in binary, and I would love, I don't know, when I first did this was a little bit difficult for me, but to figure out what exactly I was supposed to do, but yeah, I eventually managed it. So first of all, we are going to view the instruction definitions, and as we can see here, we can actually and we are also, I don't know, we are able to edit these, right? We can, for example, call this one cont instead of condition, I guess. Does it work? Cont, yes. But we don't want to do this for now. So what we want to do is we want to take these instructions. We want to immediate the value 5. And we can now see that this byte corresponds to the instruction immediate value 5, which will, let me check this again. To which register do we immediate? Yeah, to register 0. Look now. Yeah, we are not going to use black for this because this is confusing me right now. So we are going to use some purple, I guess. Purple is a great color. here we are. So this instruction will immediate value 5 into register 0, right? So the next thing we would have to do is copy. We in fact could, and if we remember right, yeah, this one is the input. We would put it into register 1, I guess. So yeah, this one is the input, and the copy command takes the input. And since we're supposed to add 5 to the input, we would have to move the input to one of the registers, either 1 or 2, since the next thing we are going to do is, first of all, we're going to move the value in register 0 to register 2, which corresponds to this instruction, right? And we can, this is actually these are actually the two highest bits, right? They are controlling our decoder, while the other two are, in case of copy, whilst in case of condition they do other things. In case of condition, they define the way the condition is met, or in case of calculate, they define the way the ALU is behaving. Yeah, in case of copy, they define the place where we are going to oh, there's a register missing. Where did it go? Where we copy from and where we copy to. And since the ALU is calculating by performing calculations on register 1 and register 2, we would have to take our input, put it in one of these registers, and then take our immediated 5 and put it into register 2. And the next thing we're going to do is we are going to perform a calculation. And compute, right? Yes, compute, add. Perfect. And this this byte, right? This instruction. These are 8-bit instructions, by the way, or rather, this is a 8-bit architecture, right? Maybe you are familiar with 64-bit architectures. Maybe you have just heard about it. This is a 8-bit architecture because it takes 1 byte, 8 bits, as an input. As an input. Yeah, this one performs our calculation, our add 5 on these 2 registers and saves it into register 3, which we are, now this is register 3, this is our input, and we are going to put it into output. These, I don't know, I just remember these. It's just, I don't know, it's just what it is. You would, I don't know, I guess you could just try. Instructions are still confusing me, but yeah. Instructions. Copy register 3 to outputs. Oops. You do not go here. And in theory, we would then add a condition. We would immediate 0. Yeah, this is perfect. And then we would Wait, which register is the one that we are using to override the counter? Yes, it's here. And then we would have to jump back to our zeros instruction, right? The first one. Condition. Always. This is always right? No. Let's see, I don't remember everything. He is always. Wait. Yes. Because of this. And I think we actually don't have to add this instruction to our program because the way it ticks. Or the way this level is handled by the game is it just runs the program until a calculation was correct and then it starts the program anew. But in theory this would take us back to the beginning of the program every time a calculation has been performed. Maybe let's actually check if this is necessary. I mean, this would work anyway because the program would run all the way through and then perform the calculation again. Okay, look, we can still see it. It never reaches the last two. It just takes the first 2, 3, 4, 5 bytes of instruction and then it ends a cycle and this the same thing again. And before we are going to jump to the next level, I'm going to show you step by step what is happening. Maybe you're interested in that. So the first byte or the first instruction is the immediate instruction, which we can see here saves by activating the save pin on our register 0 the value and also feeding the value 5 into the bus while simultaneously deactivating everything else. Yes, that's basically what is happening. So the next thing that is going to happen, this is also so fun. This is so cool that you can look at this in detail and just see everything that's happening. What is our next instruction? Let us try to, I'm not quite sure what we did next. I think we took the input, right? Yeah, we did. This is a copy command. And oh, we can also see that also, yeah, right here the register 1 is being addressed by our purple line, and this line is accessing the input, saving it into register 1, and here we are copying our input into register 1. So the next should be the copy 5 into register 2, which we can have a look at as well. Right now we are in copy mode again. We can see that. And wait, no, we are back at, oh, this is now, yeah, now we're in copy mode again. Never mind. Every time I click on things, it resets the program, which is a little bit unfortunate. So I'll have to explain without clicking on things, I guess. So here we are. The decoder is active. We save to register 3 and load. This upper bit is load, or this upper input is load, and feed the value into the bus. It goes all the way because the bus is interconnected to register 3, to register 2, and the next instruction is going to perform our calculation on these two guys. Oh, and interestingly enough, it is important that input is in register 1. I didn't even realize, because I didn't expect negative numbers to be of relevance. I've just forgot about it, but look, if this value was to be in... No, it actually wouldn't make no difference. Never mind. It's not a subtraction, it is an addition. But if, in case, like, if we were to subtract... Oh, wait a second. Let us have a look at the last instruction. We just performed the calculation. The next one is going to send it to the output. Oh, we cannot have a look because it jumps back to the first line. Never mind. The last instruction is just, I don't know, it's copying from a register 3. We can see here again. Into the output. So this was this level. Now we're going to calibrate laser cannons. On our ship, we naturally shoot incoming asteroids with lasers. In order to calibrate said laser, we want to calculate the circumference of the asteroids using an advanced equation. 2 times pi times r. R is the input. And you're going to approximate pi as 3. Which is very fortunate because, yeah, well, as I said, it's going to be quite difficult to perform calculations with how are they called? How are they called again? Rational numbers instead of naturals. Send the answer to output when it has been calculated. Yeah, of course. Also, we now have access to assembly programming. It allows you to add names for instructions. So you can, for example, type add instead of inputting 68. Yeah, this is great. Look. And yeah, let's rename these 0 to 1, or rather R0 to R1. This one is going to be named R0 to R2. I wish there were shortcuts for this. And this one is going to, oops. I just deleted register 3 to out. Now we're going to have to look at the instructions again. Where were they? There. Because I cannot do this from memory. There was a time where I was able to do this, I think. Yep, this should do the trick. Register 3 to output. Save. We are going to need some more. Than these. Comment below calculates. By the way, just writing the number immediates the value. I don't know, maybe it is we can actually look at this in the manual instructions. De Morgan's law. No, similarly we can't. Assembly. Yes. Oh look. They also, I don't know, assigns a name to the byte offset and the line it was inserted on. This is especially useful for naming jump destinations. Finish. You can add, oh yeah, this is amazing because it, I don't know, it gives you a relative number, right? Instead of, we're gonna come to this. Yeah. Oh, and we can also define constants by using the word const, which is amazing. can add, subtract, multiply, integers, divide, modulo, or and XOR together using, oh, this I didn't know as well, respectively. Breakpoints can be added by clicking on clicking to the left of the line number. The program will automatically pause breakpoint. Yeah, I don't know, you can have a look at this. I kind of know how to do it. You can set breakpoints like this, and yeah, well, the program will automatically pause. Let's put one here. Doesn't matter. We only have one instruction at this point. This is the add instruction. First of all, we are going to get the input, and we need to define this as well into R1. This will make sense. Well, this was copyright. Input would be this, and R1 would be this. I hope this is correct. Let's have a look. No, this is into R1. So what's next? By the way, these defined assembly commands are basically just representations of these 8 bits, this 1 byte. So what is next? We would have to immediate a value, and then we would have to move. Yeah, this is the only one that we would have to. Define in addition to the ones that we already have. It basically gives you the 0 to the answer right away. Now we take our input, put it to 1. First of all, we are going to immediate 6 because 2 times pi equals 6. Wait, never mind. We are going to multiply, right? It is not like, no, we are not going to add, we are going to multiply. So this is going to be interesting. We're actually going to need a label, I guess. Because we're going to, yes, we're going to have to, okay, we're not going to move you to R1. We're going to move you to a different location. So this is copy, correct? Yes. Put it into which register? Register 0. We're going to put it into register 4 because this is the only variant that makes sense. 0 to R4. Right. Save this. What are we going to do next? Into R1. Then we're going to move R1 to R2, which we have to define. Let us have a look at the instructions. I don't want to make mistakes. R1 to R2, because if we make mistakes, it's going to be messier to figure out which instruction was defined wrong. I have to be really careful when you're defining these instructions. R3 dot. So here we are. This is that. Where 4, 3. So now what stage are we in? We take 6, put it into register 4. which is the amount of times we're gonna have to add our value. Alright, okay. So the next thing we are going to do is, since we have our input, we're actually going to copy it to R0 as well. Interesting. R1 to R0. Because we want to store it, right? And the reason for that is that we are going to next add together our two values and then move register 3 to register 5. Wait, does the register 5 actually exist? 1, 2, 3, 4, 5, 6. Yeah, register 5 does exist. Fortunate. We're going to put it into R3. This is copy. The input is register 3 and the output is register 5. This should be correct. R3 to R5. Let us check this before we make a mistake. R3. Look, we nearly made a mistake. This is the correct way to define the instruction. Sorry. Right. We already saved this. So we are going to store the result of our addition into register 5, which is then sitting here. We're going to make a comment. Store initial value, initial input in reg0. And this one, number pi times 2 into 4. Right. And this was input to R1, respectively R2. It is unfortunate that we cannot just loop right here, because we're not going to take our input and yeah, anyways, we now add the two together. And now we're gonna have to check. Now we are gonna have to reduce our count by 1, which is our count. We can define count 6, constant count 6. Reduce count by 1. This is going to be defined and repeats addition. We're going to have to first of all check if count is 0. Wait register is checked by the condition register 0. So we're gonna have to, the best thing we could do is keep the count at 6. And 0, count to 0. And instead of moving the initial value to register 0, the initial input, we would store this one into register 5. This makes more sense. Or register 4 rather. Copy R1 into R4. This should be correct. Great. R1 to A4 to R4. Store initial input into R4. Right. Okay. Now we do the addition and move the result into 5. Now we reduce by 1, which we do by, oh, what is this? Blender is opening out of nothing. Maybe this is a sign. Maybe I'm going to take a break and finish this program in the next video. Maybe not. I'm gonna take a break anyway.